Hi everybody, I am Arindam. Welcome to Canvas tutorial. And today I am here with a very important topic, which is not only important from your NET and GATE perspective, but also sometimes in interview you will find question from this topic. That is a nucleophilic attack on the cyclohexanone system. You can see over here. Which attack is preferentially happening, axial attack or equatorial attack? Okay. So axial attack means you know that in cyclohexane system these bonds are called the axial bonds and these bonds are called the equatorial bond. Now the point is that if the nucleophile comes from this side, which is called the axial side, then it is called the axial attack, and when the nucleophile comes from the below side, it is called the equatorial attack. Now what happens in case of the sodium borohydride? It gives hydride equivalent, and that hydride equivalent will basically come from actually it has two opportunity. I mean, it has the option of coming from the upper side and the below side, but which one is happening in the major quantity, so that we will see over here with the explanation. So let's see actually what actually happening over here, that if this hydride equivalent over here, the nucleophile is this attack from this side, so that will be basically the axial attack. And due to that axial attack, what you will see, you will obtain that this will be O minus, and after the workup what you will end up with, you will end up with something like this. This is a hydride, that means the nucleophile itself, and the OH. Now OH is in the equatorial position, so this is forming the overall equatorial alcohol. Now the ring flipping is not happening because of the presence of the tertiary butyl group, which actually locks this conformation, because tertiary butyl group cannot be in the axial position. If the ring flipping take place, then that will be in the axial position, which is not the stable condition at all. So this is one possibility, and there will be another possibility, and that is something like that H minus attack from this side, that means the equatorial attack of the nucleophile. It's not like that the hydride is attacking. Actually this sodium borohydride moiety, it's a BH4 minus moiety is coming, and from here you will see that this kind of attack is happening, but we can think that this hydride equivalent is coming, so this is the effective in the nucleophile. Now it is coming suppose from the equatorial side, so if it comes from the equatorial side, what we will end up with, something like this. Now the hydrogen, that means that incoming nucleophile comes from the equatorial side, and we will end up with the axial alcohol. So this is the axial alcohol. This axial alcohol comes from the equatorial attack of the nucleophile, and the above molecule is the equatorial alcohol. This equatorial alcohol is obtained from the axial attack of the nucleophile. Clear? Now which one is the major? Experimentally it is just observed that this one, that means the equatorial alcohol, is the major product. This is the major product. Now some of you can argue that if we compare the stability of the product, this OH obviously a bulky group, okay, so it will try to occupy the equatorial position, so it's obvious that the reaction will end up with the major quantity of this molecule. So this can be explained on the basis of the stability of the product. But point is that we cannot discuss this reaction on the basis of the stability of the product itself. Stability of the product cannot control the reaction pathway or the reaction mechanism. Why? Because you know that just before the GATE examination I have already made a video on the Hammonds postulate. Okay, did you remember that? If you haven't watched the video, you can check the link in the description box. I have already put the link there, you can check it from there. So what actually happens in the Hammonds postulate? In Hammonds postulate you can see that it says that suppose energy profile diagram of a reaction is like that. From the y-axis I will be putting the energy, okay, free energy, and in the x-axis I will be putting the reaction coordinate, and this is somewhat the starting material, and suppose this is the product. Okay, so if it goes via a transition state, which is somewhere like this, So what it actually says that this is the maxima of this energy profile diagram, and this is the minima of this energy profile diagram. It says that the maximum of the energy profile diagram, that means this transition state, resembles with the nearest minima. Now for this assembly, the nearest minima is this one, because this is also one minima, this is also another minima. So transition state will look like starting material and not like product, okay, or the more resembles will more look like starting material. So if you compare the stability of this transition state, you have to compare on the basis of the starting material stability, not on the basis of the product. Now the scenario is completely changed for now. This is, you know, what kind of reaction it is. It is basically you can see this is the energy of the starting material, this is the energy of the product, so there is energy gap, product is more stable. So from here you can say this is the exothermic reaction. So for exothermic reaction, the stability of the transition state is explainable on the basis of starting material and not on the basis of the product. But the scenario is completely different if I see this reaction. This is basically endothermic reaction. This is endothermic reaction. Why? Because this is the energy of the product, this is the energy level of the product, and this is the energy level of the starting material, and reaction coordinate in the x-axis, whatever. So you can see that the transition state, you can see this transition state, this is near to this minima. So the nearest minima is the product. So in this case, the transition state look like product, okay, and that is why the stability of the transition state will be explainable on the basis of the product. So for endothermic reaction, transition state resembles with the product. For exothermic reaction, transition state resembles with the reactant. Now for this reaction, experimentally it is found that this reaction is exothermic in nature. It is exothermic in nature, and that is why what is happening, you will see here that for exothermic reaction, the transition state stability is explainable on the basis of the starting material. So now we cannot say which one is the major product, which one is the minor product, because this reaction is going via transition state. Obviously a transition state will be there. So this reaction goes via transition state that looks more or less likely the starting material and not that much it resembles with the product. So that is why only on the basis of the product stability we cannot say which one is the major or which one is the minor. Clear? So this theory just cannot say anything conclusive about the ratio of the product. Now Felkin interestingly proposed one more thing, that the angle strain theory. Okay, now it is proposed by Felkin. What it is actually, he says that, well, obviously there is two hydrogen in the axial position, and there, if nucleophile comes from this side, there will be some amount of steric repulsion, or rather more correct term is 1,3 diaxial interaction, which is basically a steric interaction. Okay, so when the nucleophile comes from this side, there will be a steric interaction. Okay, all right, that is okay, but it's not like that. If the nucleophile comes from the equatorial side, then there will be no steric repulsion or no such repulsive interaction will be there. It's not like that. What Felkin says that there are two hydrogen. Okay, these are the two hydrogens in this adjacent carbon atoms with respect to the C double bond O, and from the Bargy-Dunitz trajectory, it says that if there is a C double bond O, so now the nucleophile, if want to donate electron density to the pi star of this C double bond O molecule, so that this pi bond is broken and the carbon nucleophile bond is forming, then this approach is not the perpendicular approach. It says that the nucleophile comes at an angle of 107 degree with respect to this plane. Okay, this is the approach of the nucleophile. Wherever it is coming from, either from the upper face or from the lower face, that will be coming at an angle of 107 degree. So if you just consider this plane, okay, this is a, you can think that this is a planar system. Okay, so if you see this plane, now from here, if you want to draw 107 degree, so this is basically the 107 degree whenever equatorial attack is happening. Okay, so whenever equatorial attack is happening, so nucleophile comes from this side. Okay, so whenever nucleophile comes from this side at an angle of 107 degree, so now these two hydrogen are present. So these two hydrogen will be present in the eclipsed position. Okay, it is parallel and eclipsed position, and that actually is not that much favorable condition for the nucleophilic attack, because this is a repulsive condition. There will be repulsion, and that is why, due to this eclipse strain, that nucleophile will try to attack from the upper side. That means the from, you know, that is the axial attack will be there. Although there is steric interaction or steric hindrance, but the more prevailing effect is this strain. So it was proposed by Felkin. Okay, it was proposed by Felkin, but later on Cyclohexanone gave a more precise model, and that is quite acceptable also. So that is not on the basis of this one, I mean this angle strain, rather it says a complete different molecular orbital approach. Now how we can just introduce MO approach in this reaction? You know, you can see over here, this is the structure of the cyclohexanone, locked cyclohexanone structure. Tertiary butyl group is present in the 4th position. Now he says that two possibilities. Okay, one possibility is the nucleophile comes from the equatorial position, and the other one, nucleophile comes from the axial position. Now I will draw both of them one by one. So suppose I am drawing this equatorial attack in the yellow ink. Okay, so if equatorial nucleophile attacks, so that will end up with something like this structure, and if axial attack of the nucleophile taking place, then this will be something like this one. Okay, this is what is happening. Now what Cyclohexanone said that, now just focus on this carbon nucleophile bond. This is a sigma bond. Okay, if this is a sigma bond, then where the sigma star will be lying, it will be exactly in the opposite direction. So the lobe of the sigma star orbital, which is a vacant sigma star orbital, anti-bonding orbital, so that will be in the opposite side. So this is a lobe of the sigma star, major lobe of the sigma star. There will be a minor lobe in this side also, but if you consider the sigma star orbital, so the major lobe of the sigma star orbital will be something like this one. And you know, for this case also, if this is a newly formed bond, carbon and nucleophile, carbon nucleophile bond, so its sigma star will be exactly in the opposite direction. So this is a bigger lobe of the sigma star of the carbon nucleophile bond. Okay, now you can see, if you just compare these two structures, you can easily see that from here this sigma star is parallel with this carbon carbon bond. This is a carbon carbon bond, so this is a bonding structure, sigma bond. Okay, so it's a bonding orbital, so there will be some amount of stabilizing interaction like hyperconjugation or donation can be occurring from this carbon carbon bond to the sigma star. So this is one kind of stabilizing interaction. Interestingly, stabilizing interaction is also present in this case where 2CH bond is in the axial position, and they can easily interact with that one. Hyperconjugation like interaction will be there. The bond bonding orbital of the CH bond, there the electron density will be donated to the sigma star of the carbon nucleophile. So it's not actually the donation, it's actually the delocalization, just like the hyperconjugation. So these two interactions are the stabilizing interaction. These two are the stabilizing interaction. Okay. Now point is that which one is facile? Obviously carbon-carbon bond, the electron density from donating from the carbon-carbon bond is much lesser than the electron density donation from the carbon-hydrogen bond. Okay, so this is undoubtedly much favorable interaction. So this interaction is a much favorable interaction because this CH bond, okay, this bond is performing just like in the carbohydrate chemistry there will be anomeric effect. Just like that, this kind of sigma star is vacant and that is in the parallel to this bond pair, and that there will be the electron donation, which is a stabilizing interaction, and much favorable donation occurs for the CH bond, and that is why this is the main driving force for the axial attack of the nucleophile, because axial attack of the nucleophile will yield more stabilization through the molecular orbital theory. Okay, so it is the more stabilizing, and that is why nucleophile comes from the axial side. Although there will be 2 hydrogen in the axial side, but still nucleophile will prefer to come from the axial side. Clear? Now one more point is that what will happen if we just add some bulky substituents. It's not necessarily be so bulky, it could be simple methyl also, and see what will happen when NaBH4 is there. Now in this case the steric repulsion will be prevailing, and that is why appreciable amount of the equatorial attack will be occurring, and that will be the major product. Okay, that will be the major product. In this case the steric repulsion or the steric effect prevails. Okay, now one fantastic reaction is there, and that reaction is something like this. It's a norboron like system. Suppose there is a C double bond over here, so it's a norboranone. Now if you consider this norboranone, both the sides are actually equivalent side, okay, symmetrical side. Now if I add some NaBH4, okay, some nucleophile NaBH4, so that hydride equivalent can attack from the either side, so it doesn't matter from where it is attacking. So in both the cases that will be a same product because it's a symmetrical molecule. But what will happen if I add some electron withdrawing group in this position? Remember this electron withdrawing group in the below position, and that is why they will not possess any kind of steric interaction over here. So if the steric interaction is a prevailing factor for this kind of attack, then there will be obviously a 50-50 product will be obtaining. Okay, so we can think that the nucleophile can come from either this side or from the other side, because that should not be the factor, because the electron withdrawing group or that group, whatever the group is, whatever the nature of this group is, that is present in the below position. So there is no steric hindrance in this position, in this side. So from here the attack is as facile as this side. Okay, so we should get, I repeat, we should get 50-50 mixture, but it's not happening. It is basically not happening. Rather, what you can see that this one is the major product and this is the minor product. Now the reason is why it is happening. Simple thing, it's not a steric factor. It cannot be the steric factor. Steric factor is not operating over here. Then how you will just explain this kind of observation? Now to explain this observation, again you need to think about the Cyclohexanone model, just like the carbon nucleophilic sigma star orbital. So here you can think like that, because Cyclohexanone model is so helpful to just deduce this kind of explanation. So this is the carbon nucleophile bond, and over here in this side it is the sigma star of the carbon nucleophile bond. Here also this is a carbon nucleophile bond, and here it is the sigma star of the carbon nucleophile bond. Now in both the cases you can see that the sigma star is present and it is eclipsing on these two carbon carbon bond, and here also this sigma star is in the eclipse position with this two carbon carbon bond, and that is why there will be a stabilizing hyperconjugation like interaction. Stabilizing interaction, electron donation can take place. Here also electron donation can take place. Now I think some of you has already guessed that what will be the possible logic, because if there is the electron withdrawing group in this position, so that will eventually decrease the electron density. Okay, so electron density in this position will be decreased, and that is why this electron donation to the sigma star is less favorable. Okay, this donation is less favorable as compared to this one. Okay, because this is the electron withdrawing group, it is in the these all are sigma bonds, so there will not be a resonance, so obviously that will be inductive effect, and inductive effect is distance dependent. So this carbon carbon bond is at higher distance with respect to the electron withdrawing group, so this carbon carbon bond has some amount of more electron density, and if it has more electron density, then that will be a more favorable donation. So more electron density will lead to the more favorable donation, and that is basically yielding the major product like this. It's very important concept, and it was explained by Professor Govardhan Mehta, which is a leading researcher in India. So it's a fantastic work that clearly explains the Cyclohexanone model, the basis of the Cyclohexanone model, and that is basically saying that how MO theory is important to explain the reaction mechanism of organic chemistry. I hope you enjoyed the video. If you like my effort, then don't forget to share and subscribe. Thank you. Happy learning.